Assalamu alaikum. This is module 1, week number 2, lecture part 1. Today we are going to talk about digital image representation, and in particular we are going to talk about what do we mean by image resolution and image quantization and sampling. So the contents of the lecture will be talking about how how humans perceive the images, light and the electromagnetic spectrum, image representations, sensing and acquisition, finally sampling and quantization and resolution for an image. So let's get started. First of all, we have the best vision model that you can get, and this is thankfully from God. So the light falls from the cornea, then into the lens, and the retina perceives the image. Now we have around 8 to 7 million cones and 75 to 150 million rods, which are one is responsible for the color and the other is responsible for the intensity. So the cones are connected around the fovea and are very sensitive color rods, and the for color, sorry, the cones, and the rods are for illumination, which is dark and light. Now, if you can see here, so there are some optical illusions. If you look here, you feel that you are seeing a square, but actually there is no square. If you look here, you feel like you are seeing a circle, but there is no circle. These are all tricks in your mind. If you look at these two lines, you feel that this line is longer than this one, but actually both lines are the same. Same over here. If you look at these lines, you feel these lines, one of them having different angles, but actually they are all parallel lines. And if you look here and look carefully, you can see circles within the image, but these are all optical illusions. Okay, optical illusions. Now if you look here, you feel this is a three-dimensional image, but actually it's a two-dimensional image. But this is all again optical illusions. This is how your brain starts playing tricks on you. Now, in the following slides, we will consider what is involved in capturing a digital image in a real-world scene. So we are going to talk about image sensing and representation, sampling and quantization, and resolution. So image representation. An digital imaging system or an image is represented as a matrix of pixels. The origin being here as 0, 0, and this is your x-axis. Sorry, back. This is your x-axis, and this is your y-axis. So this is row 0, column 0. This is row 1, column 0. Row 2, column 0, and so on. So this is your rows, and this is your columns. Your x-axis always is your rows, and your y-axis represents your columns. So the pixel values are most often gray levels. If you have a gray image, then you have your numbers from 0 to 255. In this case, we have 2 to the power 8 resolution. Now remember, 0 will be black, while 255 will be white, as discussed earlier in week number 1. So to represent an image, we use a function which is f of xy. Now this f of xy represents the value f at the pixels or coordinates x and y. This is a scalar quantity. This is a scalar quantity whose physical meaning is determined by the source of the image. Now consequently, f must be non-negative and not infinite. So f is greater than 0 and less than infinity. You cannot have a pixel value which is negative. You cannot have a pixel value which is infinity. Your pixel values should be greater than 0 and less than infinity. So the function f of xy is characterized by two main components, which are the illumination amount and the reflection amount. The illumination of the source and the reflection of the object. So these are the main thing. If you have good illumination and good reflection, you get high intensity. So appropriately, we need to know what is the illumination and what is the reflection components of an image. So illumination is I of xy and reflection is r of xy. These are the values representing the image. So the value of any pixel is basically the multiplication of the illumination multiplied by the reflection. Keep in mind that the illumination will have a value between 0 and infinity, and the reflection will have a value between 0 and 1. So at the end of the day, whatever your number is will be always between 0 and 1. So thus the reflection is bounded by 0 and of total absorption and 1 for the total reflectance. The nature of the illumination source depends on the source, and the reflection is determined by the characteristics of the image. These expressions are applicable to also images formed by transmissions and illuminations through mediums such as X-ray and gamma rays and MRIs, like we talked about this in the previous week. So these are some examples. So in a normal day, this is the sunlight. It's 90,000 luminous per meter square. This is how the illumination on the surface of the Earth from the sun. It decreases to around 10,000 on a cloudy day. Now, in an evening, the moon yields around 0.1. Sorry, this is 0.1 luminous per meter square. In an office like this room I'm sitting in, it has around 1000 luminous per meter square. On the other hand, if we talk about the reflection, a black velvet will have around 0.01 value, a stainless steel will have 0.65, a flat white wall will be around 0.8, a silver plate will have 0.9, and snow will have 0.93. So reflection is between 0 and 1, illuminous between 0 and infinity. So to create a digital image, we need to do what? We need to do sampling and quantization. Like any analog signal or any analog value, to change it into digital, we need to do two things: sampling and quantization. So this figure shows the continuous image, and we want to take the values in respect to the coordinates of x and y. So to digitalize it, we need to have samples of the functions of the coordinates and also the amplitude. So we need to have samples, and at each sample we need to quantize the value like we are going to see in the next slide. Here you can see between the sections A and B, which is around here. See here, it is white, high. So this is the region over here. Then it becomes darker, it goes down a little bit, then higher. Over here it becomes more lighter, then dark again, then light once more. So this is it. It becomes dark, a little bit high in the middle, then becomes dark once more, then becomes back high again. So this is the intersection from A to B. This is how it is shown in on the x and y axis. Now if we start taking samples over here with space which is predefined, which is we call the sampling rate. Okay, so we start to take samples. Notice that there are some noise in the picture, so we start taking samples. Once we get the samples, we start quantizing the samples based on the quantization level. As you can see, we would start dropping the values over here and give them based on the quantization level. So we end up with this digital image. Now a few things to notice. If we have more quantization levels, we are going to get a better signal over here. If we have more samples, we can represent our image more and more. Everything is the same like we did in any analog and digital signal. Quantization is the y-axis over here. So if I have 8-bit quantizations, I will have 2 to the power 8 levels, which is 256. This is this one over here. Let me clear this one. This one over here is a 3-bit quantization because we have 8 levels and so on. The more bits you have, the better you get, the more intensities you can get out of your images. So you can see here, starting on the top, we start with continuous images and we start taking our samples. You can see here we take samples. These two mostly white, so they are converted. These two are mostly converted to white, as you can see over here. This one will take this gray and so on. We get this image at the end one by one and we convert the image. This is the actual image. This one with a low resolution 3-bit sampling, and the sampling rate is very low. So you end up with such an image, a blurry image, which is not useful. So image representations, first of all, let's represent a continuous image as a function of variables s and t, and we convert it into a digital image by sampling and quantization. So the digital image will be f of xy, the continuous image will be f of s and t. Now f of xy contains m and n rows, so we can say that the image is an n by n size, where x and y are discrete coordinates and they will have the values from 0 up to m minus 1, and y will have from 0 up to n minus 1. Remember, our coordinates will start over here. This is our origin, which is 0 and 0, and this point is m minus 1 and n minus 1. So these are our values and the range will be between these. So for example, the value of a digital image at the origin 0, 0, the next coordinate is 0, 1. The notation 0, 1 is denoted for the sample in the first row and column number 1. Okay, first row and column number 1. Now, in general, the value of the image coordinates are denoted by f of x, y. We need to specify, if we need to specify a specific coordinate or pixel, we go for I and j. This is the notations that we are going to use throughout the semester, and we are going to use them all in MATLAB. Now, how do we represent the images? First of all, we represent them using the x, y, and z axis, as you can see here. Now, this image, you can see that f is plotted as the z axis. This is f. We plot f as the z axis, where f represents our image or pixel values. Now, so this is a grayscale image with x, y, and z. This is the first representation of an image. The second representation of an image is shown over here, where we are going to use. You can see here that we have, these are black, which was the value of 0. These are gray, which will take the value of 0.5. And these are white, which will take the value of 1. So this image will have 3 values, which are 0, 0.5, or 1. So as you can see here, this is a different type of images. At the first glance, you can see and understand what this image will do. So this is the easiest way to perceive an image, to understand an image. This is the best way to understand an image. It's even easier than this method. The third and final method is representing the image as a matrix or an array. And you can see here that this is the representation of the image. These are the zeros, which is these. These are the 0.5s, which is the gray part over here, and the ones representing the D are over here. Now, this representation is good when it comes to image processing and running these in the computer. So I will finish part 1 over here and will continue with you in part 2 later on. Thank you for watching.